eet105, Chapter 12, Problem 10. Find the current necessary to establish a flux of 3 times 10 to the negative fourth Webers in the square core series magnetic circuit. Okay, so here's what makes this a series magnetic circuit. You have a coil wrapped around this part of the core, and then it's going to create a magnetic loop right here. That's what they mean by series. You have two different types of cores here. This lighter color is a cast iron. The darker color is a sheet steel. You're given that the length, this is not I, it's L. L of the iron core equals L of the steel core, which equals 0.3 meters. Now L is this distance here plus this distance here plus this distance here. And they're symmetrical, so they end up being the same, but they don't have to be the same. The area throughout is the cross-sectional area. If you cut away one of these cores, is 5 times 10 to the negative fourth meter squared. N is 100 turns. So everything's in meters here. You don't have to do any conversions. First thing you do is you take your flux density equation. You're given phi, and you know what A is. Okay, so you just divide them and you get 0.6 Teslas. Now, from figure 12.7, what we're looking at, I gave you guys a copy of this. This is it's a chart, and it's a normal magnetization curve for three ferromagnetic metals. Cast iron, cast steel, and sheet steel. So if you're given H or B for any of these materials, you can look them up. Okay, you can, graph it. So if we go back to our number here, B we found to be 0.6 Teslas. So on here we go to 0.6, and we know that, I think we were talking about, what was it? It was iron. It says it's 2,500 ampere turns per meter. So we go back to the chart. This is iron, 0.6 Teslas. We go across here, and then we hit the chart right about there. And they're estimating that to be about 2,500. That's about right here. And it looks about right. And then from the other, this is an expanded portion of that curve, this figure 12.8. It's like this little section right here. So it's blown up. So going back to figure 12.8, H of steel, it says is 70. And that would be at the same flux density, 0.6 Teslas. So let's go back to that. 0.6 of cast steel. Or no, that was sheet steel. I'm sorry. Sheet steel is this curve right here. And then 0.6 would be about right here. And if we go straight down to there, they're saying it's about 70. I would have guessed 80, but that's okay. It's not super precise. That's 20, 40, 60, 80. And then I would have picked this line about right there. They're saying it's a little bit less than that, which it is. So maybe it's 70. It could be about 75. Again, it's like an estimate. So from those two figures, you get what H is. And then this is Ni equals HL of iron, H times L of iron, which you looked up the H of iron, and then plus H times L of steel, only because these are two different materials. If it was one material, let's say it was all iron, then you wouldn't have had to look up the steel, and then I would be H times L of iron. You're given N as 100 turns. You don't know what I is. I is what you're looking for. It says find the current necessary. So N times I and then you can factor out the L because it's the same length. That was given to be 0.3. So you take that 2500 plus the 70, which would be 2570 times 0.3. And then you do algebra, you divide this side by 100, divide this side by 100, you get this. So it's 771 amps divided by 100, 7.71 amps.